Hello and welcome everyone. So today is our third community event. This time it's going to be me, and I'm going to be talking about how are differential equations truly equations of differentials. Now, this is a topic that we are trying to tackle in the Summit team, like the community team that that's participating in the 3 Blue 1 Browns Sum of Mass Exposition competition. And I just wanted to give a talk about like the topic overall, so that essentially like all the team members are up on one page, and that we can kind of then turn that, what I'm going to be talking about today, into a mass communication video that of course will look much better than what I'm going to try to do. Now, I'm going to be doing this beyond research style. So it's kind of not like your talk where you just kind of lay back and you listen and you have PowerPoint slides. I'm going to be developing the topic together with you. And that, of course, only works if you are participating. So this talk will require your active participation. And we're going to be developing the topic together. Then, of course, I now have a range of different levels of knowledge, right? This is also something that I kind of want to account for. So, of course, I'm trying to cater to as many of you as possible. And those of you who are already familiar with differential equations, of course, they will be able to understand kind of more things, and I will be throwing in a couple of things that you've probably not heard about, but you will be able to connect them. Whereas if you're like a complete beginner and you've never ever heard about what a differential equation is, then of course like this will be a little bit over your head. So everyone should kind of, listen, focus, try to participate. And if you then realize, okay, there is something going on that's completely over top of my head, that's perfectly fine. I mean, try to take away then the easier stuff, the more basic stuff, which is for you. Okay, awesome. Let's get started. I've already said that there are 3 parts to this talk. So the first thing is we're going to be looking what is a differential equation, or as we like to abbreviate that in maths, is an ODE, which stands for ordinary differential equation. Now, maybe to those of you who are already familiar with the topic a little bit, why is it called ordinary? So now it's the time to unmute yourself and to share your thoughts. It's not a kind of, oh, I know, I can answer. Maybe even if you don't know, think about it. Like, why would I call that an ordinary differential equation? Maybe what would be a non-ordinary differential equation? No clue? Well, what other types of differential equations have you heard about? Usually starts with a P.
I'm not sure, but partial differential equation.
Well done. Well done. Exactly. So this is partial differential equations. Now, do you know what the difference is? Like what we call one ordinary and the other one partial, maybe?
I think partial differential equations are with multiple variables or something like that.
Well done. Yeah, perfect. That's it. So when we look at ordinary differential equations, we're looking at something that is just a function of one variable, usually time, right? Or like we interpret it as time. It doesn't have to be time. And partial differential equations are about functions of multiple variables. Yeah. So this is why we call it ordinary. Yeah. So again, this is already for those of you who are familiar with it. Right, let's start looking at ordinary differential equations. And now let's kind of think, well, where have you actually encountered that? Like everyone has actually already encountered differential equations. You might have just not been aware of it. So I don't need a particular example. Maybe can you just tell me the field? Maybe let's start with that, where you've, for the first time, encountered ordinary differential equations, even if you haven't known that it is a differential equation. And again, that goes up to those guys who are already a bit familiar with it. Of course, if you don't know what an ordinary differential equation is, then you might even not know that you've encountered that. But that's going to be a nice surprise. So where have you encountered ordinary differential equations? Probably, I mean, in the UK curriculum, it would be year 10.
Finding the rate of change of a function.
Brilliant. That is not the differential equation, but when we are looking at solving that, the converse, so you know the rate of change and you want to find the function, but that's not the thing that you really encountered with, right? Because for that, you already needed to know how to differentiate, etc., etc. So, okay, I'll give you a second hint. It's in physics. And there are two answers that you could give me in physics. One would be a year 7 answer. No, hang on. You've not been doing that until also like year 9, year 10. This is where this should have been happening.
Finding acceleration and
not finding acceleration, but the converse, right? So if you were given the velocity of something, so you had something that is moving with a velocity, let's maybe think about a car, right? So you had a car. You had a car and you were just said, okay, bicycle. And you said, oh, it's moving, it has this velocity, right? You had velocity and you were asking for the displacement. So this is that's a point where you found where you've already encountered a differential equation. Now the question is, why is that a differential equation? Nave, why is that a differential equation?
I think it has to do with the fact that velocity is the rate of change of displacement.
Exactly.
And therefore, yeah.
Yeah, well done. So that's it, right? So if I'm looking at displacement, I know, well, how is the displacement velocity related? Velocity is the rate of change of displacement. And therefore, you have the time derivative, right, of displacement. All right, you have time derivative. Now, of course, at that time, you've not been writing it like this. You've been writing it in this way, delta S over delta T. Where the delta just stands for change, right? So rate of change, as it says. So that means I'm looking at the difference and I'm dividing it by the time taken, and I'm getting this. But what we are really concerned about is this, right? So ds over dt. Maybe what is the difference between this and this? So maybe let me use a different color. So what is the difference between delta s over delta t and ds over dt?
So as you take the limit of delta s over delta t and delta t tends to 0, you get ds by dt. Like for very small values of delta s and delta t, you get the derivative.
Brilliant, right? But that is now kind of a mathematical explanation. What's the physics difference? Like they have two different meanings, right? What is the thing that I've circled in green? How is that called?
The average velocity.
Well done. That's the average velocity, right? So this is average velocity. And the blue one is?
The instantaneous velocity.
Oh, well done. Even in a chorus. Yes. So this is instantaneous velocity. Right? That's what's happening. And average, of course, just takes an average, and instantaneous is in a moment of time. Now, this is a tricky question. Physics, like when we look at the physics, what does it mean at velocity, the rate of change at one moment in time? This is something funny. We will come back to that in the second part. And of course, there are also lots of kind of philosophical discussions to be had, which we're not going to be doing here. Okay, so this is in fact the very first time when you encountered differential equation, you were given a constant velocity and you learned the Seward equations, right? So you had like equations that said, oh, this is how you calculate displacement from a velocity, right? But what you were actually doing, you were solving a differential equation. That's the only special case that you were considering, because that's the only one that you could do at that time, is that the velocity is constant. So therefore, the average velocity is the same as the instantaneous one, because it's the same all the time, right? But secretly, you were solving a differential equation. Now, you could say, okay, but this is a bit artificial, right? Usually I need to know how much I traveled to be able to calculate the speed or the velocity of an object. So this seems to be like, you know, like a silly exercise. And I would agree, but there is another thing that you encountered in physics where it's actually not a silly exercise, but it's actually the main problem, or one of the main problems in physics that physicists have been considering. I'll also give you a hint, it's in mechanics. And this is actually the main reason and the main drive for studying differential equations. Do you know what I'm talking about? Not quite sure. Okay, to not get stuck on this topic, because we really want to get going, let me just tell you, it is Newton's second law. Now, why is Newton's second law, why is that related to differential equations? So let's kind of write it. F equals ma. So that is essentially the godfather of all differential equations that you consider in physics, and also why, of course, researching differential equations has become so important in mathematics. And of course, from this law, this is also what led other physicists, and not just physicists, but also biologists, economics, yada, yada, yada. Okay, whenever we used a so-called mathematical modeling of so-called dynamical systems, that we like to use differential equations. Now, but maybe quick explainer. Why is it that Newton's second law is the godfather of all differential equations? Well, because it's so important. It's the fundamental law of mechanics, or one of the three, right? But how is that related to differential equations?
Sorry, Professor, could you repeat that?
So why is Newton's second law related to differential equation? How? What is the exact connection here?
So it's stated as the rate F is equal to m dv by dt. You can, that is how you can relate it to differential equations. There's also like the formal definition is something like the rate of change of impulse is directly proportional to the rate of change of momentum is directly proportional to something. Let me just recall that.
That's fine. We again, at the moment, I'm not too fussy about the physics side. The key insight here is that acceleration is the rate of change of velocity, and velocity, of course, is the rate of change of
Yes.
position, and therefore we get the second derivative, right? So the second rate of change of position or displacement is acceleration, right? And well, why am I saying that this is fundamental, whereas the thing about the velocity sounds a little bit artificial? Well, the reason is because forces, they come from interactions between objects. This is where the physics happens, right? And Newton said, well, whenever there's physics happening, there is acceleration, right? There is a rate of change of velocity. And that means if you know what interactions are happening, then you can go and predict how an object should be moving by solving this differential equation, right? So this works kind of in two ways. But here I'm particularly interested on the way that said, OK, I have my physical theories, I have my forces, I know how objects are interacting, and I have models for these forces. And now I am asking, well, if I give you the forces and I know the interactions, how is the object moving, right? And that is what's happening here. And that is the main drive for differential equations, okay? So yes, everyone's seen differential equations already in physics quite early on. You were just not aware about it, right? You were not just aware of what's going on. And that's perfectly fine, right? So it's a more sophisticated tool. Of course, it's also mathematically much more tricky. So therefore, this is kind of introduced later. But this is something that Newton had to think about very carefully, and he did. This is why he came up with the idea of calculus. And at the same time, also Leibniz has been thinking about these same things. Kind of, OK, if I have non-constant velocities and non-constant accelerations, how can I solve for knowing the positions? And this is what led to the development of calculus, right? So these are the physics motivation behind the whole of calculus. All right. OK, so now we spent now quite a bit of time kind of trying to understand what we've already, where we heard about differential equations. We see that differential equations have something to do with knowing the derivative and asking for the function, right? So this is what is actually going on. So I'm given the derivative. That's what Araf said. And I'm asking what is f, right? So I'm not given f, I'm getting the derivative of f. Right. Now, if you've not known about differential equations, that might now again be a little bit on top over your head. So let's move on and actually try to understand differential equations and actually the key things, the most important things about differential equations by looking at something that I like to call the river problem. And this is where you can understand essentially what differential equations are about. So what is the river problem? So let's say we have a river. Okay, the river is flowing, and we start measuring its velocity. So at each point on that river, I can measure its velocity. And then I'm drawing in little velocity vectors like this, right? So that would kind of describe how the river is flowing, but it just tells me the velocity. Okay, let's keep it like this. So I'm knowing the velocity at a point. So maybe I'm going to this point and I know the velocity, right? And what I want to predict is that if I have like a little floating object, maybe like a little piece of cork, and I'm throwing it into the river at this point P, how is it going to move? What path is it going to follow? Now, how would you figure out that path? just from my drawings, which path is it going to follow?
We could follow the arrows.
But how? Like this? The arrow is pointing in this direction?
We connect the arrows, the different arrows.
So I'm connecting them, okay. But then how? Because they are like pointing in different directions. Okay, I will draw a curve, right? It's going to follow a curve, and I think everyone is kind of clear, right? I'm asking silly questions. Oops, it's actually not that easy to draw. Right. Or here, it would be following, again, not so easy to draw in one go. Right, here it would be following this kind of path. But what is special? What is special about this path? Like, how is this path related to these arrows? Maybe let's zoom in. So let's say I'm making a little zoom in here. So we make like a zoom in. So you indicate that with a magnifying glass. So we're looking at what's actually happening. And what is happening here? Say I have these velocity vectors, they do this. And I now want to draw this green curve. How is this green curve related to these blue arrows?
We join the arrows, like adding vectors.
Okay. So let me do that. So am I doing like this? No, I'm joining the arrows.
Something like that, but smooth.
Smooth, but what does it mean? So it's not like this. It's more like this, right?
Yeah.
It's smoother. Okay, so how is the arrow? So again, let's imagine that this is my point P. And here I have my velocity at point P. And let's give our green path also a name. Let's call it gamma. For no particular reason, we just like the gamma. So how is this vector v, the velocity vector at the point P, related to gamma?
Dr. Ba, I'm going to have to rejoin in 2 minutes. Is that fine?
Yeah, go for it. They are tangent, right? So tangent. That's what I'm paying attention to. Okay. So it's tangent. The vector is a straight thing, right? Is a straight piece of line. The curve is curved. We kind of follow them, but what does that really mean? It means they are tangent. Okay, that's what it means. Right. So that is our river problem. Now, how is the river problem modeled by a differential equation? For that, we now need to piece together all these different pieces of information that we had. So we said, okay, we first need to know the velocity at each point. on the river, then we need to, if we want to trace out the path that an object is going to be following, we of course follow these different arrows. And we know that the way to do that is that whenever I'm drawing such a green path gamma, then all the arrows have to be tangent to it at the tail, right? At the point where they start. So that's the tail of those arrows. This is where they have to be tangent to the curve. Now, can we maybe relate it to what we've been talking about before? Okay, I see OneNote hates me, so I will need to reshare because it's refusing to show the full picture. So just bear with me. And while I'm loading it again, you can think. So how is that related to differential equations that we've been talking about here? Can someone maybe draw the connection?
You know that the velocity will be the rate of change of the green path at that point.
Okay, very good. So what we would actually know, if I'm like the rate of change of the green path is a bit odd, right? Because the path is a path. The path has to be tangent, but it's true. There's already a second step. I'm saying, okay, the path is the path that, say, my cork, my little piece of cork or my little leaf that I'm throwing into the river is going to follow, right? Then it's true at every point, the velocity of that little piece of leaf or of the cork would actually have to be equal to the velocity of the river, because the river is carrying that piece of cork along, right? And that's also what we've been seeing before, right? Velocity related to displacement. But now I need to turn that into a mathematical formula, right? I need to write down something mathematically, and we just pin down the idea because the idea is important. So the velocity of a point particle following my path gamma, right, has to be equal to the velocity of the river flow, right? So how the water is moving. So that's what I'm looking at. So this is essentially, this is my idea, right? This is my idea. I need to now express it mathematically. And when I try to express it mathematically, I first kind of need to pin down what kind of object is this. Mathematically, how can I model this idea of having all these velocities at different points? What would that be? What would that be mathematically? That is what is called a vector field, right? At each point, in of the river, I have a vector, right? So this means, in terms of the mathematical objects that I'm using in maths, this would be a function, right? It's a function. So I first need, hang on, I want to use this first. So we call that a vector field B. That's what we're going to be talking about. So that is the very first ingredient that we need to have. And what is that vector field? That vector field is a function. That function needs to have a domain of definition. And the domain of definitions, of course, are going to be the points in the river. So I'm just calling the set of all points, right? The set of all points here, I'll just call that U. That's the collection of all points in the river that I'm interested in. So these are the all set of all points on the surface of the river, because honestly speaking, I'm just talking about the surface of the river. Right? And then I need to know what is going to be the so-called codomain. So where does this function take its values? Any suggestions?
Reals?
Reals, the proposal is reals. Well, reals would mean that I'm giving it numbers. But look at it. Am I giving it numbers?
Isn't velocity just a number?
It is if it's one-dimensional.
Ah.
How many dimensions does this problem have?
2.
2, right? So indeed, coming back to the school thing, we've learned, oh, velocity, you know, is just a number. It's not quite. It's not a scalar, right? Remember, you might have had that in school where you distinguish between vectors and scalars, right? And a vector has a direction and magnitude. A scalar has just a magnitude. Well, direction in one dimension is just plus minus. Am I going in the positive or in the negative direction? But here it's two-dimensional, so it needs two numbers. It is a vector, right? So when I'm using the reals, I need to use the reals to the power of 2. I need pairs of real numbers, right? So I'm taking a point. The point will have an x and y coordinate, and I'm going to be mapping this point. I'm going to be mapping this point to the velocity that the river has at this point. And again, this is x and y coordinates, and this, of course, also has x and y coordinates, right? Okay, that is the next thing. Then we've already learned what a solution of this, what a wannabe solution is. The solution, right? Let's talk our wannabe solution. Is that we want to have a path, right? We want to have a path which I called gamma. Now, the gamma is the position of my particle in time. So how am I going to model this using a function? What's going to be the domain here for this function gamma?
Also gonna take in U position.
That's something that we might think, right? So we want to give it position, but remember I said this is the position of the particle in time. So what should I use here?
So then we use time.
We use time, right? And in fact, it's going to be the position, of course, is in U. That's the output, right? So it's going to take the time and it's going to tell me, well, at time, say 1 second, for example, that's the position you're going to have. So that's what's happening here, right? So this is position in time. So this is my wannabe solution. But now, what makes gamma a solution to this differential equation? Well, in fact, we still don't know what the differential equation is. And to get that differential equation, that is that we somehow need to relate this vector field to our wannabe solution. That's the condition, that's the equation that it has to satisfy when you want it to solve this ordinary differential equation, right? So the equation, the ordinary differential equation, is what needs to satisfy. And we already have a hint, right? We have our main idea what is happening here. Well, if gamma is the path that my particle takes, right, in the river, flowing along, that means that the velocity of the point particle is equal to the velocity of the river. And now I just need to turn that into an equation. I need to turn that into an equation. So when I'm reading the velocity of a point particle following gamma, what do I need to write down now mathematically? How does this statement translate into a mathematical object? So velocity of a point particle following gamma. What do I need to write down? How do I find the velocity of a point particle that follows gamma?
Is ds over dt.
So here I'm using gamma, right? I would be writing d gamma over dt at t. And we use Newton's notation. Newton, because he didn't, I mean, this is Leibniz, yeah? So this is Leibniz. And this is Newton. Newton, when he were taking time derivatives, he was looking at dots, right? So that's what Newton liked. So gamma dot of t, so the time derivative of gamma, has to be equal what? Velocity of the river. Well, here we have to be a little bit more careful. How do I translate velocity of the river?
We can use the function that we made.
So that's the velocity of the river, and then I need to give it an input. What's the input that this vector field now needs to have?
Gamma?
Yes, because the derivative, so the velocity of the particle at time t, right, should equal to the velocity of the river at that position of the particle, right? So that's what we have. And here we go. Now we can pull that together using Newton's notation. I'll write several different notations. So this is your ordinary differential equation, right? Usually we also write that without the t, so then there is v of gamma. Okay, so that is a differential equation, ordinary differential equation, quite generally. Okay, there are some caveats that I should say. This is the explicit form, not an implicit form, but that's not important for us at the moment. That is an ordinary differential equation, right? We again know, so this is what we know. We know the vector field. This is given to us. So we know at each point what is the rate of change that we expect. And this is the thing that we would want to figure out. And we have a relationship that tells us, right, if you have this rate of change of gamma, then this is the equation that it has to satisfy. And that is the ordinary differential equation you need to solve. Are there any questions up to this point? No questions? Then I have a question. How many solutions does such an ordinary differential equation have?
So we want one. I think.
Say again, we
want one, so maybe one.
Okay, one. Now let's look at this. We said that this gamma here, right? That this is a solution to the differential equation. What about this one? Is that also a solution or is that no solution?
It is a solution.
It's a solution. So how many solutions do I have for this ordinary differential equation gamma dot equals v of gamma, where v is the velocity here in this river?
We have infinitely many solutions.
Infinitely many, right? And what other piece of information do I need to nail down one solution?
Where we threw the cork.
Yeah, so where we throw it in, right? So we need the initial position, right? So I have infinitely many solutions, right? This would be another solution, okay? And essentially, depending where I'm throwing it in, I will get a different solution. So this is maybe something that we just want to take away because it's very important when we try to solve differential equations. We need to understand, right? So let's make a little triangle here. An ODE has infinitely many solutions. Right? We need an initial value. We need an initial value to nail down 1. Okay, so I need to know, well, at time equals 0, maybe the curve has to equal this point. So if I have this equation, this information, together with the differential equation that says the rate of change has to be equal to my velocity field, my vector field. This is called an initial value problem. Yeah, so sometimes abbreviated as IVP. And that is what I need to be able to get a 1 solution. If I'm not telling it the initial value, if I'm not telling it where I'm throwing it in, then could be any solution. Well, like not any solution, but they're infinitely many. And this amount of the amount of solution we call the flow of the ODE, right? So that's what we call the full space of solutions. And why do we call it flow? Well, because we think of it as a river, right? It's kind of like the whole river flowing. So it's infinitely many solutions, right? So, and that's essentially it, right? That is an ordinary differential equation. That is what we call a solution to an ordinary differential equation. And yes, it's not unique. We need to always specify an initial value so we can solve the ordinary differential equation, right? That's it. What I have not been talking about is, oh, what if I have second derivatives? Okay, that is something that I'll leave to you as an exercise, as a little consolidation problem here, right? Let's call it E1. Maybe there will be more. Maybe how do we translate F equals ma into an ODE? because the key difference here is, right, f equals ma had like second order time derivatives, right? And here we're talking just about first order ODE. So that's kind of a little thing to think about. It's actually not very hard, but I'm not going to do it here. It's a great little problem for consolidation that you can check out to see whether you understood, you know, what's really going on here. So a nice little exercise. Okay. How do we translate f equals ma into an ODE? And I'm saying when I'm saying ODE, I'm meaning first order ODE. So let me just quickly summarize. So we had this kind of river problem where we had the river flow and we were asking ourselves, well, if I'm throwing a cork at a particular point, how's it going to move through the river? If I know at every single point the velocity of the river flow. And geometrically, this is quite intuitive. Well, you need to draw it. It's going to follow a path that is tangent at every point to these little arrows that mark the velocities at this point. And if it's supposed to be flowing along the river, well, then the velocity of the point particle that is my cork, yeah, following this path, well, that has to be the velocity of the river. And then we essentially needed to translate everything into mathematical objects, right? This whole picture, this whole intuition into mathematical objects. And that leads us to the notion of a vector field, then how to model our solution, which is just a curve, right? So it has one parameter, which we usually think of as time, and it spits out positions. The vector field takes in positions and spits out vectors, yeah, velocity vectors in this case. And then we just need to translate our intuition into an equation, and that gives us how a general ordinary differential equation looks like, right? So this is a general ordinary differential equation. Okay, here it's done in 2 dimensions. Of course, if you make things one-dimensional, if my river flow would be just, you know, I have different speeds or different velocities along a line, well, then it would be just, I would be picking one-dimensional vectors, so I wouldn't only need to know whether it's positive or negative numbers. And if it's 2-dimensional, 3-dimensional, you can go to any dimensions, really, okay? So this is what a problem, a picture that I would like you to take away, because it explains everything about ordinary differential equations, right? If you understand this river problem, you're going to understand the general theory of differential equations, because that's kind of geometric picture that you can use to understand it. Are there any questions? Bruno, Princewell, any questions? Right, I'll take that as a no. I've heard Princewell, I think, saying something, but it was very silent. Okay, so that's our one picture, right? So this is ordinary differential equations. Our second part is now to think about infinitesimals, and in our third part, we're going to connect things together. So we want to think about infinitesimals. Now, what is an infinitesimal?
An infinitely small number.
So an infinitely small number. Where does that come from? Can there be an infinitely small number? Now, that's the idea. That's correct. So my idea is kind of infinitely small. It doesn't have to be a number, but let's just go with numbers for the moment, because that's what we're most familiar with. Infinitely small number. Now, can there be something infinitely small?
Technically, 0 is infinitely small.
I would say 0 is 0. Infinitely small, it's not infinitely small, it's just 0, right? Okay, you could argue with me, but 0 that is infinitely small. But we can have an argument. But okay, let's go along. 0 is because it's 0, it's also infinitely small. So this is also what we're going to be using in our definition. That's true, that 0 will belong to infinitesimals. But can there be something else than 0 that is infinitely small? What does it mean to be infinitely small? Tricky, right? It's not quite an obvious answer what that should mean. In fact, this is just something that exists in our imagination. Now, can we think about why, or can we, think of why people like mathematicians in particular here, and physicists and engineers, how did they come up with this idea that we would be looking at something that is infinitely small? Do you have an idea? Why would I even ask this question? Or like, why would I even consider something infinitely small? I have to have some motivation to do this. What do you think the idea has been?
Maybe you want to see something over a very small change in time.
That's certainly something. In general, the motivation was, if I zoom in on it, it's going to become simple. Let's look at an example here. So we see this, curvy shapes that I'm drawing, right? It looks a little bit like an ellipse, right? If it's curvy, it's complicated. But if I zoom in, right? Okay, OneNote only allows me to zoom in a little bit. So let's move over here. I see, well, if I'm zooming in, it's actually becoming a little bit simpler, because if I'm looking just at this point, thank you, OneNote, that you don't allow me to zoom in more. It's become simpler. How has it become simpler?
Is infinitesimal something sort of a geodesic? Like
Something is, sorry?
Like something sort of geodesic, like the shortest path in a curve.
So if you bring in geodesics, you're already thinking about how am I generalizing straight lines onto curved surfaces and curved space. So that is not really simple. That is just kind of generalizing a concept. That's generalizing a straight line. So it's related, but it's not. Let's just focus on my question here. What can we say about the green blob that I've drawn in? Okay. Let me do that again. So I'm going to be zooming in as much as OneNote allows me to. And now I'm saying, oh, I'm looking at something infinitely small here. So I would be saying, well, I can't do infinitely, but I can do here. In what sense could I justify that this green shape that I've just drawn is simpler than the white shape?
The green shape looks like a straight line.
It's a straight line. Straight lines, we're cool with. Straight lines are easy. We can do things with straight lines. Curvy things, more complicated. Okay, so let me answer that question. Why is infinitesimally small and infinitesimals, why are people considering it? Well, think about what do we do as humans in science. We always like to break down the complex bit into simpler parts. Right? So for example, people figured out, oh, hang on, we have all this stuff around us, but it's made of elements. And there is just a certain number of elements, right? Of course, we now discover that we can build artificial ones, but like the stable elements that we can find in nature, well, there's just a finite number of it. And we can explain everything else that we see, at least the chemistry of everything else that we see, by understanding these elementary parts and how they bond together, right? That's chemistry. And we also use that in physics when we say, oh, I want to understand the physics of a gas, for example. Then like one picture that we use, which is called like like point particle mechanics picture, right, or statistical mechanics, is to think of this gas is made out of little billiard balls. Again, simple particles which should represent the molecules. So it's just a human habit to say, oh, I want to understand something complex with something simpler. And then people were wondering about, well, if I have something like this, right, that's complicated. can I understand it simpler? And said, oh, you know, if you do the same thing that you use with matter, and I hate OneNote now that I can't properly zoom in, then it becomes simpler, you know, but it's still curved. I would need to zoom in and zoom in and zoom in, you know, because it's continuous. It doesn't matter how deep I zoom in. If it's a finite amount, it's mathematicians, as creative as they are, they think, oh, hang on, if I can't do that infinitely many steps, maybe if I use infinitely many steps. So if I'm zooming infinitely close, whatever that means, I'm not going to tell you. But then it actually becomes a line. And we know that from experience, right? I mean, look around. The Earth is curved. But if you look around you, or if you stand on the surface of the Earth, it looks flat, right? It looks like a plane. It looks simple, but it's not simple. So this is the idea. This is the motivation behind infinitesimals. So in a sense, what we want is, let me just give that a name, like atoms of the continuum. Okay, so we want something that is like an atom of a continuum, and we really like to think about straight lines. So when we think about geometrically, right? So geometrically, curvy things made up of straight lines. Right, curvy made of straight. So this means if I have this kind of notion of infinitesimal, if I can somehow make this work, then I can understand something curvy from something straight, and I can do with the straight. So that's easy for me to do with maths with. And then I hope to get something interesting about the curvy stuff. So this is what is happening with infinitesimals. But then, of course, the other big question is, okay, you have a brilliant idea. That is nice. And that's, you know, cool. But how do you make this work, right? And this is something that mathematicians have been struggling with for a really, really long time. They kind of had an intuition how to make this work. And the guy who kind of really developed this and really worked with this first was Leibniz, right? Newton as well, but Newton ended up not being very happy with it. So therefore he thought, oh, maybe that's not a good idea. But Leibniz, he was just like, oh my God, that's awesome. You know, so this is why we have this kind of notations from Leibniz that remind us of these kind of infinitely small things, which we're of course going to be looking at in part 3. Okay. So, but the problem is Leibniz kind of set up a few rules, like heuristic rules, how to work with infinitesimals. But he was never kind of able to give a proper mathematical definition. No, who cares? You know, like Leibniz just got us started. Many mathematicians tried. Mathematicians tried until the beginning of the 20th century to give a definition of what an infinitesimal is, and nothing really worked. But physicists and engineers didn't care, and also mathematicians initially didn't care. But philosophers were getting more and more upset, because philosophers like John Locke, for example, he was saying, right, we already know from Descartes that, you know, mathematical truths should be fundamental truths. They should be obviously true. But like when you work with these infinitesimals, you sometimes treat them as 0, you sometimes don't treat them as 0, and it is essentially up to you. It is very ad hoc. So he called them ghosts of departed quantities, right? Because you could just kind of get rid of them when you didn't need them, and you kind of work with them when you needed to use them. So I think John Locke's ghosts of departed quantities is actually a really good description what infinitesimals are. Right? They're not really there, but they're somehow there, and they somehow contribute, and then they really don't. So this is all like kind of very dodgy. And mathematicians had a big problem, because at the beginning of the 20th century, with Bertrand Russell kind of realizing, oh, you know, there's those guys who try to kind of base mathematicians on a logical axiomatic foundation, so kind of a bunch of rules that we can derive all of maths from. And these rules were axioms developed by Gottlob Frege. And he said, well, you know, that's kind of nice, but I see a problem. because I can use these axioms to actually derive a contradiction. And you might want to look this up if you're interested, Russell's paradox, if you've never heard about that, okay, about the set of sets that do not contain themselves, or the barber in Sevilla who shaves all men in Sevilla apart from himself. No, hang on, have I phrased it correctly? Well, never mind. So Russell's paradox is something. No, the barber of Sevilla who shaves all men that do not shave themselves. And this leads to kind of paradoxical situations, and this would break mathematics. So, you know, mathematicians were quite desperate at the beginning of 20th century with this, and they said, oh, we need to become really more careful. And then they realized we kind of don't need infinitesimals. We can get away, you know, we can get away. We can use the notion of a limit, which you might have heard about. So why using infinitesimals? Actually, they're a terrible idea. So they abandoned them. They said, that doesn't exist. It's rubbish. Physicists and engineers have still been using them. And then it was kind of in, well, I think in the 30s, 40s, don't nail me on the date, when you had Abraham Robinson, who came up with a way of defining infinitesimals. This led to a field which is now known as non-standard analysis. And then we had Bill Lawvere and Anders Kock in the 60s, who also gave a definition of infinitesimals, which is different from the one of Abraham Robinson, and leads to a you know, field of, that is called synthetic differential geometry. Okay, now we're going to be looking at the second one because it's a bit more geometric, right? That's what we're going to be looking at. And we're going to be using infinitesimals as developed by Lawvere and Kock and many others, but they were the kind of, they started the field. So as you can imagine, I mean, that sounds like, oh my God, you know, all the mathematicians before the mid 20th century were not able to pin down a definition. The definition must be really complicated. Yes and no. The idea of the definition is very simple, in fact. So we can introduce that, you know, in 5 minutes. That is not a problem. What is really tricky about the definition is to make it work with the rest of the mathematics. And that's not something that I'm going to be tackling today. Okay, so you need to be quite adventurous there, and you need to do really bold things, namely kind of building your own mathematical universe called a topos, and kind of show, oh, in this mathematical universe, I can make the theory work. And so it's consistent with everything else that mathematicians have been doing. You know, it's not kind of a bubble that exists independently of maths, but no, I can relate them. But this is really tricky, and we're not going to do that. We're just going to work with the so-called naive theory, right? With the intuitive notion of infinitesimals. So let's have a look at that. How can I model things? I'm going to be using my idea, and I need to turn it into a mathematical definition. It's the same thing that we've been doing over here. We needed to turn an idea, an intuition, into a mathematical definition, right? And then once we have a mathematical definition, we can do proper maths with it. You know, we can be, we are not ambiguous, we're clear, we can calculate things. That's great. And of course, also on the other hand, when we do this maths, then we're going to be guided by this intuition. So we kind of have an idea what we do when we work with these rather abstract objects, which are essentially just functions. So we now want to do a similar thing here, right? So we kind of really want to go along this idea that we're looking at an atom, and it should kind of geometrically turn curvy things into straight things. So now let's look at a particular example. Right. Wait, let me draw a grid here. So that's going to be our x, and this is going to be our y. And then we're going to be looking at a circle. Fingers crossed, I'm going to get this circle right. Yeah, beautiful. So I'm going to have a circle. And, you know, for simple purposes, we're just going to be putting the center of the circle on the y-axis 0, 1, and we're just going to say the circle has radius 1 so that it's simple. Okay, now how is it going to help us? we need to kind of relate curvy things with straight line things. Now, maybe we can already have a sneak peek over here because we've been doing that already. What was the key thing? How did we relate curvy things with straight line things when we're discussing the river problem? What was the relationship between a curvy thing and a straight line thing that we could kind of utilize here when we talk about infinitely small?
The velocity vectors were tangent to the curve.
Brilliant. The idea of tangents, right? Because again, in infinitesimal, I cannot touch that. I cannot draw that. It's infinitely small. I need to visualize that somehow else. And the idea is exactly that of a tangent. So if I'm looking, and this is why I draw these coordinates in this particular way. So if I am going to look at this point, which is on the circle, right, then I can see that this line is tangent to the circle at this point. But what does it mean to be tangent? Again, we have a geometric idea, but we have not a clear definition. That doesn't matter. At the moment, we just work with the geometric idea. And we now need to explore this geometric idea, how that could lead us to the idea of infinitesimal. Maybe someone has a suggestion. So when I'm looking at a tangent to the circle, how can I turn that into helping me finding out how to define infinitesimals, infinitely small numbers? So how are infinitesimals, how do they come into play, or how could they come into play when I'm looking at the tangent line and the circle? Any ideas?
I think by finding a straight line in the circle.
Brilliant. Exactly. If I say, well, where is the circle straight? Well, what is a tangent? The tangent should be touching the circle, right? It should be touching the circle. It should intersect with the circle. And when it's touching, it's actually like it should be intersecting with this little straight line piece that, of course, is infinitely small, right? It's infinitely small. If there is such a thing, it has to be infinitely small because the circle is in no place a line. In no place. But if I zoom in infinitely close, then I would get this kind of little straight line piece of the circle. And again, because that's how computer works, we can actually see that this is also what computers do, right? They cannot plot a proper circle. They plot like a really large polyhedron, which is made up of straight lines. And that's the idea indeed. So I said, okay, so they intersect in a very, very small thing. Let me just make it a little bit smaller, which we call D, right? So this is, maybe let me make that bigger. This D, this is where they're intersecting. Cool. So now let's just go along and try to figure out what D is, right? What can we say about the Y coordinates? Of the points in D?
The Y coordinates are going to be 0.
They have to be 0, right? And now we can come back to our infinitesimal numbers. So, the X values, they have to be infinitely close to 0. But now the question is, what does it mean? Well, let's try to figure that out, and let's set up some equations. So if I'm looking at the equation of my circle, right, then I would be looking at x minus 0 squared plus y minus 1 squared. And this is equal 1 squared, which is, of course, equal 1. right? So now I can simplify this. So I'm going to do that in the next thing. And of course, my tangent, what's the equation that gives me my tangent?
Y equals 0.
Y is equal to
Exactly.
0.
That's y equals 0. Well done. And we see, oh yeah, we have that already, right? Y equals 0. So we already used that. So this information we've already used. So that's we're done with this one. Okay. Now we kind of need to put that into this equation, right? So you need to put that into
So
this
x squared is
equation.
equal to 0.
Exactly. Well done. Right. So I'm going to go, and if I'm saying, what am I going to get? Well, I'm going to get that x squared plus 1 equals 1. And of course, that leads me to that x squared has to be 0. And because that point is not x, but is actually d, right? That gives us a definition d squared equals 0. So this is how we can define infinitesimals. So now I can go and I can basically bring it back here and said, well, d is the set of all numbers that square to 0. But if I do that, then I realize I'm having a bit of a problem. Can someone see the problem?
0 squared is 0.
It's only 0, right? But now I have to be a little bit, I have to think more carefully. For which numbers is it true that the only thing that squares to 0 is 0? It's
For
just the reals.
Yeah.
Right? So we like to have infinitesimals. If I want to have some infinitesimals that are not just 0, we have to extend the reals to get infinitesimals. I mean, that's fair. We tend to do that in mathematics. Where else have we done the same trick that we just extend the numbers when there's not sufficient enough of them?
The imaginary numbers.
Brilliant, right? There I want to solve the square root of -1. Well, the square root of -1 is not a real number, cannot be. So I just make it up. I say, oh, let's call it I, the imaginary number. So, you know, we do this trick all the time in math, so there's nothing to be afraid about. So we just go, okay, we need to add a little bit more numbers so that we have infinitesimals, right? We're not going to be looking at the details, so we're just going to go along. So, so what we get is from the reals, we get a new set, which is just the reals without this bold double, all right? Let's call that the smooth reals, which essentially behave like the real numbers, but not entirely, because they have these funny infinitesimals. And of course, that creates also problems. I promised you that there's going to be a bit more exercises for you to think about. Is why can't, let's call it, why can't I have square roots in R, right? That's something that I'm going to lose. And there's another thing that we have to be careful about. Why can't I divide by infinitesimals? All right, so these are the two things. Why can't I divide by infinitesimals? Things that you can think about. Okay, so this is the price to pay. There is no free lunch. There is a price to pay. So, okay, so now we've kind of say, okay, we swing the magic wand, and we suddenly have infinitesimals by essentially adding them to our reals to get the smooth reals. So we do that. So that's awesome. Now the question is that enough? And the answer is no, it's not enough. I need to do something else, because here I've been just looking at the circle, right? I've been just looking at the circle. But what, given any graph of a function, so if I have some graph of a function f, then I also want the same thing. I want to say, oh, look, if you're going to be looking at a point, say x naught, right? You have the respective value over here. And now you're going to look at infinitely close values. So maybe, I'm going to draw them a little bit bigger, so not really infinitely small. As I said, this is just an abstraction. It doesn't really exist. But what if I'm looking at some infinitesimal neighbor, right? So I'm looking at an infinitesimal neighbor. So of course, I'm going to get f of x naught plus d, right? And now let's look at all the things that happen in between, because all of these things, they are kind of infinitely close to x naught, right? Now, if they're infinitely small, how should f, like this function f, how should it map it? How should it map those infinitely close numbers? What's the shape that I would want to produce?
It would be a straight line.
I want a straight line. Well done. That's what I want, right? Okay, so again, I'm not going to quite get a straight line because, again, everything that I'm drawing is finite, but I'm just going to indicate that here. So that's the idea, right? If I'm saying, and I'll make it a little bit thicker to kind of ignore that. So I'm going to get a straight line. And that's the idea behind infinitesimals, right? If I have something curvy and I parameterize it, then if I'm just looking at infinitely small steps, then the curvy thing should be turning into something made up of straight lines, right? This is here back to our original idea, turn curvy things into straight lines. Cool. But that's a big claim to make, right? That's a big claim to make, and this leads us to what is called the Kock-Lawvere axiom. My handwriting is getting terrible here. So Kock-Lawvere axiom, that is something that I need. And what does the Kock-Lawvere axiom say? It says, well, give me any function that goes from my smooth reals to my smooth reals, right? And now give me any point that you're interested in the argument, right? And now take any infinitesimal step, right? So any infinitesimal step that you can do. And now when you make that infinitesimal step, then your function is going to behave as if it were linear. So that means when the function, which is curvy, I restrict it to infinitely small steps, it behaves like a linear function. And this is something that we're very well familiar with, right? Where, of course, here, this is uniquely determined. That's something I need to now put in as an assumption into my axiom, that there is such a uniquely determined thing, uniquely determined number, uniquely determined. And that is, of course, that number is the rate of change. That is what I'm calling the derivative, right? So usually when I write down the Kock-Lawvere axiom, I'm not using this notation, but here, to speed up a little bit, I've already kind of introduced that as the derivative, because that is the rate of change of the function, right? That's the gradient of the function at this point. Okay, so this is a very, very bold claim to make, because it says any function is differentiable. But then you might think about and say, oh, hang on, I can come up with examples of non-differentiable functions. Can you come up with the examples of non-differentiable functions?
Maybe a function that jumps between numbers.
Well, let's be quite particular. Let's be very simple. What is the simplest example? The square root function, right? If I'm looking at the square root function, right? So I'm taking an argument x, which of course has to be positive, right? That only works when I'm looking at the positive values. And I'm saying, well, that's going to go to the square root. That is not differentiable. Well, it's not quite true. There is one point where this is not differentiable. Where is it not differentiable, the square root function? And why?
At 0.
True. So it's not differentiable here at 0, but why?
The square root of 0 is not defined.
Oh, it is. The square root of 0 is 0.
Oh.
Well, think about what is the tangent? What is the tangent at this point to this graph?
That would be the y-axis.
All right. And the y-axis, what's the slope of the y-axis?
It's infinity.
Would be infinite, right? Like, kind of doesn't make sense. It's not really defined, right? It's also not infinite, but it's not defined. Doesn't make sense, right? I can't write this the y-axis in the form y equals mx plus n, right? So the usual form of a line. This is if I'm using this equation, and this is the equation that I'm using here, right? So I'm secretly using the equation mx plus n, where this is of course the m, right? And this is the n. Then that's not going to work for the y-axis. I can walk around these things. It's not, you know, it's not the end of the world, but it means that this is not differentiable at 0. Now, I already told you that I don't have square roots, so this example kind of is not there. So square root functions do not exist for these functions. So you see, okay, there seems to be some trade-off. Something really interesting is going on here. And this is where it gets really deep. So this is going to get super, super deep. Okay, this is where you have to go and you build your mathematical universe to make things work, etc. So it is this axiom that breaks, the ordinary mathematics, and that requires a little bit of flexibility in thinking. But it's not a huge price. I mean, if we look at it, if we take like 2 steps back and we say, what's happening here? Oh yeah, that's fine. We can go along with it. Okay, so you will never really run into trouble if you are careful. I mean, you have to be careful that you can't do everything that you've done with the reals. You can't do everything with the smooth reals. You have to be careful. And there are certain functions which certainly are not given anymore because, you know, the square root is not defined for infinitesimals. You can think about why. Okay, so that's what we need to know about infinitesimals, right? So this is part 2. Thinking about infinitesimals, we said, right, at the moment, out of the blue, we want to think about infinitesimals because we want to explain the idea of differential equation. Why is it kind of really an equation of differentials, which we're going to tackle in the 3rd part. And we just talked about infinitesimals. What is the core idea here? Well, I'm thinking of infinitesimals as infinitely small things. I'm thinking of geometrically of straight lines. So I'm thinking if something is curvy and I'm zooming in infinitely close, it becomes a straight line around every point. And that's something that we wanted to now model mathematically. So we were looking at the example of a circle, which we put into a nice coordinate system and turned into equations. And we said, well, if you want these infinitesimals to exist, then you have to accept numbers that square to 0 but are not provably equal to 0. Right? You can't prove them to be equal to 0. Bear my words, I'm using them very wisely here, but I'm not going to kind of go into details. What's going on there? There's lots of sophistication. The attention is, or the devil is in the detail here, right? Okay, so I need those numbers to square to 0. And of course, the reals don't do the job. Oh God, when I go and extend the reals, okay, fine, you go and extend the reals. But what should happen to every other function? right? And you say, well, for every other function, I'm very bold. I'm going to claim that I can differentiate it. Or what does it mean in our infinitesimal language? That means whenever I'm looking at like an infinitely small piece on the x-axis, it's going to be mapped to a straight line in the xy plane that matches the function. And that is the Kock-Lawvere axiom, right? And I've already pointed you that that is a very bold statement because, of course, there are non-differentiable functions. How to deal with this? This is where it gets tricky. But we're not going to be looking into that in any more detail. So are there any questions about that?
Professor, I will have to rejoin in 5 minutes.
Yeah, go ahead. Right. So that means there are no other questions. Then let's move on to part 3. And that is, we somehow want to marry these two things, right? So let me make it big. So now we want to go and we want to kind of combine these two things together. All right, we want to understand this infinitesimal notation. Now let's have a look at this. Here we've already seen kind of infinitesimals. But here we do something that we can't do in our mathematical model of infinitesimals, and that is dividing by things. I mean, we can't divide by infinitesimals. That just doesn't work with our model. So, but they do appear, right? So it's the idea, the infinitesimal rate of change. So that's something that we now want to exploit and then apply to differential equations to see, what can we do with it? And what can we do with that idea? So let's look at equations of differentials. Equations of differentials. Now, first of all, what is a differential, right? What is that? That is an infinitely small difference. So infinitesimal difference. Right? Now let's look at that. So we would, for example, write it as dy. What is y? Well, usually we write y equals f of x, right? So this is when we think of plotting a graph of a function, I'm writing y equals f of x. So what is dy? Well, that's an infinitesimal difference. Well, what infinitesimal difference? Well, I could look at the value of a function an infinitesimal step d away, and I could subtract the original one, right? So essentially, let me just kind of go back to my picture here, all right, to my picture here. So if I were to plot things over here, let's use blue, right? So that's f of x naught, and that's f of x naught plus d, right? So what I'm really looking at is this difference here. That's infinitesimal. So they're also infinitely close. So they're infinitesimal neighbors. So that's what I'm going to do here. I'm going to just write it this way. F of x naught plus d minus f of x naught. Right? And then I can continue because I know, well, if I'm looking at my axiom, right, this is just the derivative times the step d. Right, so here I'm going to use the Kock-Lawvere axiom, which I'm abbreviating as KL. Now, if I'm thinking of the d, this is, let me just do that in green as well. So the d, well, this is just x naught plus d minus x naught, right? So this is an infinitesimal difference in x. So I can use that as well, and I can simply rewrite things as f prime of x naught dx, right? Okay, so let's piece that together. I just said that for my function, the infinitesimal change in y, this is just f prime of x naught times dx. Okay, everyone with me so far?
Yeah.
Yeah. Right. Now let's apply that to ODEs. Let's go and do that. So let's go up here and look at our ODEs. Now we need the definition of our ODEs, right? And we see this. That's what's happening. So let's rewrite this definition, or maybe let's just go through the steps one by one so that it's a bit more clear. So what I'm looking at, if I want to know the infinitesimal change of the particle trajectory, right? If I want to know the infinitesimal change of the particle trajectory, I'm going to look at the particle some infinitely small time step away after t. And I want to know the displacement of that particle. So I'm just going to be subtracting what is happening at t. So let's plot that. So here there is gamma t. Here is the position of my particle. Or maybe I should have actually used green. So let me, since I used the green before, so let me rewrite that just using the green. Oops, there it is. Okay, so gamma t plus dt minus gamma t. So that is an infinitesimal displacement, and I'm plotting this again. So here I have gamma t. Here I have gamma t plus dt. And I'm saying this is d gamma. Right, so this is d gamma is just the infinitely small displacement vector between these 2 points, right? And now we can apply once again KL, our axiom, and that axiom is going to tell me, well, this is just the time derivative of gamma times dt, right? So that's what it says. It says d gamma equals gamma dot t dt. And that's awesome, because let's translate what this actually means in geometry, in geometric terms. So if again, now I'm kind of zooming out, yeah, so I'm zooming out. Maybe I'm going to use a different color. I'm going to zoom out here. Yeah, so zoom out. Then what's actually happening, I have my particle trajectory, right? And then I have my tangent vector, right? Which is the derivatives is here actually a tangent vector at gamma t. This is where it sits. And now what I'm saying is, if you take this tangent vector, which of course I could go and I could plot the tangent line, right? If I have the tangent vector, then I could just go and say, right, let's plot the whole line, at least indicated. That is a tangent line. And now I can ask the same question. Oh, what's the intersection between my path gamma, which is the curve, and this tangent line? And well, what the definition of derivative in terms of infinitesimals tells us, it says, well, you just take this tangent vector and you just multiply it with an infinitesimal time step dt. That's what you do. And then you get, oops, here, then you get, this is gamma dot, okay, I need to write bigger. So this is gamma dot t dt, right? So this is the infinitely small time step. So if you take the vector, which is of course 2 real numbers, right? It's big, it's something I can draw. And I am multiplying it with an infinitely small time step. Well, this is actually, maybe I'm going to be putting it here. This is actually this straight line, d gamma, right? So this little displacement vector, this infinitely small displacement vector, can be calculated from my derivative that I've calculated and then just multiplied with an infinitesimal time step dt. So that's the one part of the equation, right? So here we've just written out what the derivative is. Now that's kind of step one. Let's do step two. So this is step one, and this is step two. Let's bring in the differential equation, right? So we're saying, well, gamma dot of t is actually a vector field which describes my river flow, and it's actually the velocity vector of the water at this point gamma t, right? That's what's happening. So let's bring that in. Let's bring that in as well. So now we have, if I'm kind of combining this with 1, so if I'm bringing in my result in 1, I have that d gamma equals gamma t dt. Well, but gamma t dt, this is v of gamma t dt, right? And here we go again. That is now an equation of differentials, right? So the differential equation here is actually equivalent to this differential equation here. I'm going to be writing that again. So if I'm looking at differentials, then that's the equation of differentials. Now you might wonder, okay, fine. How is that helping me, right? What kind of insights can I gain from describing the differential equation in these terms? Actually, quite a lot. And the most important thing is this picture here that we've drawn under 1. Because look at that. Look at that. Look at our equation. It says, well, if you tell me the starting point, so this would be here the starting point, right? And I know the velocity, well, then I can calculate the infinitely small displacement that the particle has to make in the next time step, dt. Of course, the time step is infinitely small, which is something that we will tackle now in a minute. But that's what it says. And this is marvelous, because just taking this different point of view, right? Just taking this different point of view, I have an idea how to start solving differential equations in general, right? And I mean, there's been lots of things covered today in this session. So you might kind of be like, oh yeah, right, fine, okay, now I'm going to be solving them. But what I would recommend here is to really kind of take a step back, go back to what we've been doing here, and try to think, well, how would you solve these differential equations if I'm not giving you geometric pictures, but if I'm giving you a particular differential equation, like a particular vector field v, and said, okay, this is the vector field, find the solutions. How would you go about it, right? So this is something that you should just really think about. And how could you go about this in general? Oh my God, that starts sounding really difficult. Like, how am I going to go about this? How am I going to do this? And with this picture now, we actually get an idea. We get a hint how we can go about this. So let's explore that. So how does that help me? So that's the big thing. So helps with finding solutions. Okay, that's the great thing that I can do with this by looking at the differential equations from an infinitesimal point of view. Okay, I can go find solutions. Now, the sad ending of the story is you're not going to be able to calculate these solutions, but at least it will give you methods how to compute them numerically. Okay, because the sad news about differential equation is even though we can prove that solutions exist, that doesn't mean we can tell you how you find them. And at the end of the day, you have to do things numerically, right? You can't just go and calculate the solutions exactly. You have to calculate approximate solutions using computers, using numerics. And that's what we are going to be looking at. We're going to be looking at the so-called infinitesimal point of view very naturally. Because what does this infinitesimal point of view tell us? Well, it says, well, let's imagine we're starting with our initial point P, right? This is where we throw in the cork back into the river. This happens at the point P. Now, we know that there is a velocity that it has to have, right? And we, of course, know from our equations, right? We know that this is, or at least, well, no, we know exactly that this is actually gamma dot of t. And then we can say, right, so if I'm starting with this, different color, if I'm starting with this and I want to know, well, what is then the next position after an infinitely small time step? Well, let's just look at our thing. It's going to be gamma t, right? So I'm rearranging this equation. Maybe I should do that very quickly, right? So we get, this is gamma t plus dt minus gamma of t equals v of gamma t dt. And now I can just rearrange that. And I'm going to get gamma t plus dt is gamma t plus v gamma t dt. That's what we're going to get. So now I can do the same thing again, just here, and just substitute. Well, okay, so this is now v of p. Well, I know what this is, and of course I need to multiply that with infinitesimal time step dt. But the great thing is that I know this value, right? Gamma t is just p, right? Because that's, sorry, I mean one step ahead, which I not paid attention to. Of course, I need to start with my initial value. So this is gamma 0. So I can go and can say, right, this is p plus v p dt. Okay. Well, that's awesome, because now I can calculate the next step of my particle from the information that I've been given, the initial value, the vector field, yeah, so and of course this time step dt. But the problem here is, and this is the kind of, again, the problem here is only works infinitesimally. And we said, well, infinitesimals is something that we imagine. That's kind of not a real thing out there that I can really work with, right? Only works infinitesimally. So how is that really helping me? Well, it helps me in various ways. One thing, and I'm just going to be stating this, if you repeat that infinitely many times, right? So if you kind of think about, you have p, and then you would have gamma 0 plus dt 1, then you would make another infinitesimal time step, another infinitesimal time step, and another infinitesimal time step, you know, and you have these infinitesimally small displacement vectors d gamma, which you can calculate from the vector field. The vector field just tells you, well, you know, here you have a d gamma 1, here you will have an infinitesimal displacement d gamma 2, here you will have an infinitesimal displacement d gamma 3, etc., etc. So if you now kind of sum them up, so this kind of continues, I'll probably use the bracket to kind of continues these things. If you kind of keep summing them up, well, and if you do that infinitely many times, if you integrate them, if you form an infinite sum of infinitely many displacement vectors, then you will eventually get to the final position. So you could say, well, mathematically, if I perform like an infinite sum of these infinitely small contributions, if I want to get to a point, which we mark here, so somewhere here, right? So this is now gamma t plus delta t. So the delta is now like a proper real number. It's not infinitesimal, but it's a proper real number. All right. So here I'm going to use. Then you have to form an infinite sum, right? You have to form an infinite sum. So I need to do an infinite sum. But what is the infinite sum of infinitesimal small things? How do we call that?
An integral.
That's an integral, right? So I can now go and I can do something very important. I can write, say, okay, if I want to get from t to delta t, or maybe I'm messing notation. Let's just call it capital T. So the final time, yeah, or T1. Let's call it T1, right? So we want to get to T1, and this is of course gamma of 0, right? So if I want to get to gamma T1, well, then I need to start with my point at gamma 0. I need to start with an initial point, and then I need to integrate from 0 to T1. And what do I need to integrate? Well, I need to integrate just all these d gammas, right? But what is this d gamma? Well, we know what this d gamma is. We have our equation, right? This v gamma t dt. So this is just gamma 0 integral 0 to T1. And here I can write, well, this is just v gamma t dt. So I now turned the differential equation into a so-called integral equation. And I could celebrate. Now I can say, yes, now I can solve it. Not quite. Because, look, I want this, but this appears here as well. So you still turned it into an equation. So this is called an integral equation, which is equivalent to the differential equation. Right? It's equivalent to it, but it just doesn't tell you that you can solve it, but it leads you to many, many important ideas how you can develop solutions. So this kind of rewriting of the differential equation, so between the equations between differentials, right, allows us to turn it into an integral equation in a rather straightforward way. And we also understand what is happening. And because we understand what is happening, we can develop many things. And one of the things that I can develop, and this is where this is the last thing I'm going to do, is this Euler method. What is the Euler method? Well, I can't do infinitely small steps, but I can do finitely many steps. So here, what's the idea? Replace the infinitely small with a finitely small delta t. Okay, it looks like an F. Let's write that again, like delta t. So turn dt to delta t. Okay, that's what I can do, right? I can do that. Then it's not exact anymore, because here the infinitesimal things only work if it's exactly an infinitesimal small step. But if it is a finite step, then it's not going to be exact anymore, but it's going to be a good approximation. So then I could say, right, if I want to know what gamma is at the time step delta t, and I make delta t very small, right, a very small value, what that means always depends on the problem. Then I can say, well, now because delta t is not infinitely small, but a finite time step, I can still say, well, I'm actually at least getting an approximation. Right, I'm at least getting an approximation, so I can calculate it. What has been an equality here for infinitesimals just becomes an approximate, right? So this just means approximately equal. So this just means approximately equal. And here I can just continue. Well, this is just gamma t plus v using the differential equation, gamma t delta t. And now I'm in the same fortunate situation because I have this, I know the previous time step. Maybe I'm starting with t equals 0, then I'm at point P, right? So this would be, again, I'm at point P. Then it tells me, well, this is where you would be roughly. So this is roughly where you would be at t plus delta t. So that was going to be my new time step. And then you apply that again, and you apply that again, and you apply that again. And infinitely many time steps, you get these kind of polygons, polygons, right? Polygonal path that is an approximation to the real one. So the real one, of course, would, okay, let's maybe, the real one would do maybe this. Okay, well, it's actually is also not quite true. The real one still needs to be tangent here, right? But maybe it just does this. And that's the important thing. It can actually turn really bad. So this numerical method is actually not the best method. It is very prone to error. It's very unstable. But it's a first step, right? So if I now want to go and if I want to solve differential equations on a computer, then I have a method, right? I have an idea how I can do that, right? How I can do that with finitely many time steps. I'm not going to be able to find the exact solution. Fine, but I'm going to find an approximation to it. And if the approximation is good enough, then this is sufficient for my model that I'm trying to calculate, be it a simulation like beacon motion on the screen, be it that you actually want to simulate something, you know, you want to make predictions, how a system is going to develop in time. It's going to give you something. Of course, then again, you have to look into the itsy-bitsy details and understand what is the how far away are you from, like what's the estimate of the error that you're making and things like that. This is, of course, something that you need to consider if you start looking at professionally. But again, that goes beyond what I wanted to present in this talk, right? What we see here is the Euler method, how I can turn the fact that a differential equation really turns out to be an equation between differentials. So the name differential equation just doesn't come from nowhere. No, they were aware of it. Like when it's been introduced, then people knew, oh, what you're actually looking at is an equation of differentials. And we can make that precise with our infinitesimals. When we do, then we realize that it leads us to a way how we could technically solve a differential equation. You need the initial value. Then the differential equation gives you the infinitesimal displacements that you have to follow, and you now have to sum up infinitely many infinitesimal displacements, which means you have to solve an integral, and then you can find the new position at time t. But of course, again, that is not really feasible, right? That is not really feasible. Why? Because it's an integral equation, right? The gamma t, and if I just wanted to solve this integral, I have the problem that it appears on both sides of the equation. So this is in general kind of not a solution, but another equation. But it's a really good starting point to develop solutions. Okay, I can start using this to really develop solutions for differential equations and to develop the theory further. And the other thing that I can do is I can say, right, even if I'm not getting the exact solutions, if I am turning the infinitesimal dt into a real big delta t, which of course should still be small enough, so it's not infinitely small, but it's small, then I can actually use this insight to construct a numerical solution, so an approximation to the solution which I could run on a computer. And this in principle allows me to solve any differential equation numerically on a computer. All right, I think let's stop that here. Are there any questions? Silence. Who's been completely lost now? Raise your hand on team. Who's been completely lost? No one. Good. Not bad. Well done, guys. Okay. It's kind of lots of things have been happening. So well done for keeping up. Right, so once again, are there any questions that you want to ask? Right, I can see no questions. Of course, you can always ask questions on Discord later on. So very well done. Well done for your contributions. A big special thank you to Araf, who's been contributing a lot. Well done, Araf. That's it then. That is the third community event, which was now, of course, very different from the other two that you have seen. So thanks for participating, and I'll see you on the server. Bye-bye.
Thank you, sir.
Thank you.
Yeah, thank you so much.